everybody. Today we have Charles Korn talking about embedding Golang in a Kotlin app. Charles is a senior engineer on the Mimir team at Grafana Labs, with particular interest in developer experience, automation, and cloud-native infrastructure. In today's presentation, Charles will outline his experience when he tried mixing Kotlin and Golang, and why doing so was almost certainly a bad idea. Please welcome Charles.
Round two. Thanks, everyone. I begin today by acknowledging the Wurundjeri Woiwurrung people of the Kulin Nation, the traditional custodians of the land on which we gather today, and pay my respects to their elders, past and present. I extend that respect to any Aboriginal and Torres Strait Islander people here today. As you just heard, my name's Charles. I'm an engineer at Grafana Labs. I'm interested in a bunch of different things, including developer tooling and open source. I'm a maintainer of a bunch of different open source projects, including Protect and Camel, and contribute to many other projects. While Grafana has been very generous in allowing me to come today and giving me time to do this, this is completely unrelated to everything I've been doing at Grafana, for reasons that will become obvious shortly. This talk is all about something very unusual that I've been doing recently, the idea of embedding Golang in a Kotlin app. And before I get into the inevitable question of why on earth I've been trying to do that, and explain why it's a terrible idea, I'm going to talk about the concept in general, break it down into a few smaller problems, and talk about when those problems might actually be relevant and be a sensible thing to do in the real world. And of course, there'll be plenty of time for questions at the end. So let's start at the beginning, and let's start with the big picture of how this all works. How can a Kotlin application call a Golang function? The whole problem really boils down to one thing: the magic of C interop. What do I mean by that? Both Kotlin, both the JVM and the native flavors, can call C functions. And Golang can both call C functions and expose Go functions as C functions. And so we can take advantage of that and use C as a bridge between Kotlin and Golang. This technique is not special, it's not unique to these two languages. Like, you can use this to bridge lots of different languages. Almost every function has some way to call C functions because of the fact that most operating systems expose themselves as C functions. So things like Python and Ruby and .NET can all call C functions. And then many others, including Rust, can expose functions as C functions, so they can be called by anything that can call a C function. But for today I'm going to focus on Kotlin and Golang. So how does this work? How can Kotlin call a C function and therefore call a Golang function? Throughout this presentation, I'm going to use a really, really simple example of a Golang function that takes in someone's name and gives you back a greeting for that person. It's sort of a classic hello world kind of thing. At a high level, it looks a bit like this. First of all, we need a C function to call, and the C definition of it looks a bit like this. It takes in a pointer to a char, so it's a string, and returns another string. As I just said before, Golang can expose Golang functions as a C function, and so we can use that to provide the C function that we need. Unlike what we normally do with the Go code and turn it into an executable application, like a binary, we can build that and package it up as a library. So we can package it up as a shared object or a DLL or a dilib, depending on which operating system you're using. Or we can make it into a static library, which we can then build into our application. On the other side, we then need to call that C function from Kotlin. On the JVM, we can interoperate with any C function through a bunch of different libraries I'll talk about in a bit more detail later on. With Kotlin Native, the support is even built in, so we don't even need a library, which is awesome. And we can directly call any C function thanks to its built-in C interoperability. So now the problem decomposes down to these two parts. One is exposing Golang code as a C function, and the other one is then calling that C function from Kotlin. So let's start on the Golang side. How do we expose a Go function as a C function? The first thing we need to do is define our function. How many of you are Go developers, by the way, or familiar with Go? Most of you? All right, for those of you who aren't, I'll quickly explain what's going on. So this is a definition of a function. It's called generate greeting. It takes in a single parameter of type c.char and returns another parameter that is a pointer to a C char. And then all it does is then format in format a string that has a message, hello from Golang, and then the name that you pass in. Yeah. Those of you who are Go developers will instantly notice that the parameters are not using the ordinary Go string type. They're using this pointer to a C char. The reason for that is that Go has very, very strict rules about memory management, and in turn has very, very strict rules about using strings because of the way that the string type is constructed in Golang. And so therefore you have to use a special C type rather than the Go type when you're passing strings back and forth. And so that's what's going on here. All right, so we've got our function. It will return the value that we need. We do need to do a couple more things to make this available to the world of C. The first thing we need to do is add in this magic import C. This gives us all the C types we just used, in particular c.char and the helper methods as well. But it also enables CGO. And CGO is the tool that's built into the Go toolchain that enables interoperability with the world of C. Once we've got that in place, we then need a magic comment on this function that says export generate greeting. And CGO looks through any file where you import C like this, and will generate, and looks for those comments, sorry, and will then, make that available to the world of C. It'll expose it out for you. The last thing we need to make this work is a little bit of boilerplate. So if you want to expose anything to C, CGO insists that that is in the main package in Go, so we need that. And if we're in the main package, then we need a main function. It doesn't have to do anything, but it has to be there. So that's a little bit of extra things that we need there. So with all of that in place, we now have a function that can be exposed to the world of C and can be called by anything that can call a C function. The next step is to then take the source code and build it. And so again, it's not a huge change from the ordinary world of Go where we're building a binary, but instead we are going to build a library. And we need to tell the compiler to do that. And to do that, we just pass an extra argument to Go build. So there's two options here. You can build a shared library, so a DLL or a dilib or a shared object file, or you can build an archive, which is something that you would statically link into a final binary. We can run that, and Go will go off and do its thing, and it will produce that library for us, and it will also produce a header file that we can then import into our C code to actually invoke that function. So that's what it looks like on the Go side of things. Let's look at what this looks like from the Kotlin side. I'm going to talk about both the JVM and Kotlin native separately because it is a little bit different. But yeah, most of you, when you think of Kotlin, will probably think of Kotlin JVM. So I'll start there. Everything I'm about to talk about is in fact not limited to Kotlin on the JVM. It's anything JVM at all. So everything that I'm about to talk about is equally applicable to Java, to Scala, to Groovy, anything else that runs on the JVM. You can use the same techniques for this. And there's lots of different ways to do it. So I'm going to go quickly through these and talk about each of them and talk about when you might want to use each of them as well. The first and the original is JNI, which has been built into the JVM since version 1.1. It has really great performance. However, it does have the drawback that you need to write a C function of your own that translates from from C to JVM C types. And then you need to compile that C function for every single target that you have, which is a pain in the ass. If you're targeting Linux and Mac and Windows and you want to target x86 and ARM, maybe doing 32-bit and 64-bit, suddenly you've got to cross-compile this for, 6 or 8 different architectures. It's awful. So yeah, it's generally not what people do these days. The next option is JNA. JNA is an open source library and has a much nicer developer experience. So rather than writing some C to translate back and forth between the world of C and the world of the JVM, instead what you do is you write a Java or a Kotlin interface or a class for structs, and internally JNA does the mapping for you. However, there's no free lunch here. This does come at a pretty significant performance penalty. So then, of course, another thing came along that improved on that. So JNR came along. It is an open source library as well. It is quite widely used. In particular, it's used by things like JRuby, so it is quite battle tested. It has the nice developer experience of JNA, but it also has much, much better performance as well. It's still not quite as good as JNI, but it's likely good enough for most scenarios. All right, and then the fourth and final option is what's now known as Project Panama. So this is something that's in preview for the JDK. It's a replacement for JNI. It's built into the JVM. It's been going through the Java enhancement proposal process, which is quite a mouthful, for the last 2 years. It was in preview in Java 19, and will be in second preview now for Java 20. And yeah, like Project Panama is really cool. It combines that really nice developer experience that you get with something like JNA or JNR with the better performance that only something built into the JVM can give you. Another really nice thing about Panama is that it has some really nice tooling support as well. So yeah, like JNA and JNR, you need to write that Kotlin interface or that Java interface to translate things. That's still true for Panama, but Panama also has some nice tooling to generate those things for you automatically. So you don't have to do that manual work. Yeah, for the example I'm going to show in a second, I'm going to use JNR for two reasons. One, it's the thing I'm most familiar with. And the second one is that it's something that you can most readily use today as well. So let's see what this looks like in terms of some code. The first thing we need to do when we want to call a C function is take our C function definition. So this is what it looks like, to remind you. And we need to translate that to an interface. So it looks like this in Kotlin. So JNR requires that every library you want to call be represented in terms of interface for all the different functions you want to call. The method name, the Kotlin method name, in this case generate greeting, has to match the corresponding C method. So generate greeting has to be the same in both places. The parameter names, on the other hand, don't matter. What does matter for parameters, though, is that the order of the parameters has to be the same, and the types of them have to match. What is kind of cool about JNR is that, at least for method calls, it will translate Kotlin types or JVM types in general to their corresponding C types for you automatically. So we can use an ordinary string here, and it will automatically translate that to a pointer to a char. So that's the translated method. Next, what we need to do is tell JNR how to take the C library on disk and turn that into some Kotlin code that we can actually call. I'm not going to go into all the details because it is a lot, and I recognize that I'm putting a lot of code on a slide in a presentation. The basic idea is that we need to take that DLL or that dilib or that SO, package it up into our jar at build time, and then at runtime pull it out of the jar, tell JNR where to find it on disk, tell it what the Kotlin interface is, and then it will do the magic behind the scenes to map those things and make it work. With the library loaded, we can then use that library, and we can call functions from it. So for example, if we wanted to call the generate greeting method, this is a really simple application that would do that. We go off and load the greeting lib using this method above, and then we can call it just like any other Kotlin method. There's no extra sort of work required like what we saw with Golang, sorry. So, so that's what a method call looks like. Just for sort of completeness, I've also got an example of what a struct looks like. So if you're passing something more complex than just a primitive data type, you need a struct in C. So let's say we've got this C type here that represents a human. So it takes a string for a name, an unsigned 64-bit integer for age, in case you're really old, and a boolean to whether you're an admin or not. This is how that looks in Kotlin with JNR. So it's almost an ordinary class. There are a couple of key differences. The first one is that it has to extend from this special struct base class that JNR provides. The properties must use these special types that JNR provides as well. Like you'll notice these aren't the ordinary Kotlin data types for strings or numbers or even booleans. And the reason for that is that that allows JNR to do the translation back and forth to C, and take it and also consider situations like if you've got like an int in C, handling the fact that that is a different size on different platforms. The name of the class in this case, the name of the properties as well don't matter. It's just the important thing is that the order of the properties is the same as the C type, and that the types match, or at least map, back and forth. So that's the JVM. Let's look at what this looks like for Kotlin Native as well. Unlike targeting the JVM with Kotlin Native, there's only one way to interoperate with C, so it's much more straightforward, and it's built in, which is really cool as well. So let's go through the same example on that side. Again, we start with the C function definition. That's the same as before. Like I just said, given how common of a scenario this is with Kotlin Native, Kotlin Native doesn't require to do any translation ourselves. Instead, it has a tool that's built in called C interop. That's part of Kotlin Native's built-in tooling. It's built into the Gradle plugin, and it will generate the method stubs and the struct definitions for us automatically. What we do need to do, however, is tell C interop how to do the translation. So there are 3 bits of information that are really important. The first is the Kotlin package that we want the methods and the types to be generated in. So that's that first line there. We need to tell it which C header files it needs to scan to work out what the methods are. So that's the second one. And then the last one is telling it the name of the library file to statically link into our application. So in this case, unlike with JVM, we have the option to statically compile our binary. And so, yeah, doing that makes life much easier. So that's what we're doing here. All right, so then with that out of the way, we can then write an application that calls that method just like any other. Again, it looks very, very similar to the JVM example. The only difference here is that, similar to what we saw in Golang, Kotlin native does not hide the fact that you're translating back and forth between C types, and so that's why we've got these extra methods here on the string, where we call CStr to turn it into a C string, and then the 2k string method on the end there to turn that C string back into a Kotlin string, so that you can deal with it like normal. So that's how you do this. Let's talk a little bit about when you might actually want to do this in the real world. To answer, the first sort of hypothetical question is, when would you actually want to call a Go function from Kotlin code? The answer is usually you wouldn't, and usually you shouldn't. When would you want to call a C function from Kotlin code? That's more of a normal thing to do. However, I will put the caveat there that usually there is a really great pure Kotlin or pure JVM library at least that you can use to do most things. And so again, this should be an edge case. It shouldn't be a common thing. However, one particular scenario where this is a really common requirement is where you're dealing with the operating system or dealing with devices and things like that. And if that isn't exposed to you through the standard libraries, then doing this is a perfectly normal, perfectly legitimate thing to do. And the way I've just shown you is how you would do that. But if you do go down this path, you do need to be prepared for some pain. And in particular, when calling C from Kotlin, there are 2 major sources of pain to be aware of. The first one is memory management. So unlike in Kotlin, or many languages on the JVM, where we generally don't need to think about memory management, as soon as C is involved, you need to start considering who is responsible for memory, thinking about who's going to be responsible for freeing that memory, who's going to, when that's going to happen. It's not super difficult. I mean, people have been doing it for decades, but it is really error-prone, and it can be quite difficult to reason about, especially when you're thinking about mapping back and forth between the 2 worlds. Fun fact, the example I just showed you actually leaks memory. We need to free the string that we got back from Golang, because otherwise it will just sort of sit there forever. The consequences of getting memory management wrong can vary from simply just consuming too much memory, which is usually not the end of the world, all the way up to things like memory corruption, security issues, and crashes as well. The other big source of pain is the impact on the developer experience. So usually you can't use a Kotlin debugger to step into C code, for example, so that can be quite annoying. If you're targeting the JVM, you need to handcraft those interface definitions or those class definitions, and that can be error-prone, and it can be quite tricky to diagnose when you get that wrong. Of course, in Kotlin native, you've got the C interop tooling, and so that makes it much easier. And finally, you need to have an understanding of both Kotlin and C and how those 2 worlds work together. And that adds extra cognitive load, of course. So, in summary, 2 big sources of pain for calling C from Kotlin. When we add Golang into the mix, that just compounds. So memory management becomes more involved again, because now we need to consider how Golang and C and Kotlin all want to work together, and how they each manage memory, and how those things don't quite line up. To give you a concrete example, so I mentioned before, talking about the Go string type, that Go has very, very specific rules around what you can do with Go managed memory. And that makes C interop more complicated. There are certain rules about when you can and cannot pass Go pointers outside of Go, because otherwise the garbage collector can't work properly. And of course, you can't use things like a debugger across the language boundary either. But as you probably guessed from how this slide is laid out, when you add Golang into the mix, you get some exciting new sources of pain as well. The first one is around tooling. So when we're working like this, not only do we need a Golang toolchain and a Java a Kotlin toolchain, we need to make these 2 things work well together. So that either means doing something like running the Golang tooling from Gradle, or having some other alternative tool like Bazel, for example, that orchestrates the whole world as well. On top of that, CGO needs access to a C compiler and toolchain that can compile for each operating system and architecture target that you have. And for those of you who've ever tried to do that, you know that's not straightforward. And I'll talk a little bit more about that later on. Lastly, when you're moving back and forth across language boundaries, you're limited to the lowest common denominator of what's supported by each. And this has a particular impact on things like data structure design, method signatures, and can make things like callbacks and things like that quite tricky as well. So, in summary, there's lots of pain. And hopefully at this point, you're thinking like, this has been interesting so far, but like, it sounds like a terrible idea. Like, why on earth did he do this? And the answer is that I'm trading one kind of pain for another. And to explain why, I need to talk a little bit about an open source project I mentioned right at the beginning, called Betect. So Betect is a tool for managing Dockerized local development environments. It is written in Kotlin for reasons you can read about on my blog, and most of the Docker ecosystem, as many of you will know, is written in Golang. However, the Docker daemon exposes an API, or an HTTP API, that in theory should be accessible to any language, right? It's HTTP, it should be straightforward. The reality of that, however, is not quite as nice. Parts of that API are really poorly documented, or just aren't documented at all. Parts of that API implicitly use Golang conventions, use constants from the standard library, for example, and those don't map nicely to operating system constants, for example. There are parts of the API that are really non-standard, if I'm being polite, or really weird, if I'm being less polite. For example, when you go to build an image using BuildKit, the new image builder, you as the client, so in this case Betect, send an HTTP request to the daemon and say, hey, I'd like to build this image. The Docker daemon says, that sounds awesome. I'm going to take that TCP socket you used for the HTTP request and use it to send you gRPC requests. And it's weird. And of course, yeah, most HTTP clients do not support that kind of weird, having the TCP socket taken away from underneath you, which makes integrating with this really tricky. The other pain with the API is that a lot of it requires significant client-side logic that needs to be re-implemented. So things like piping container I/O back and forth is really tricky. Dealing with registry credentials for pulling and pushing images is really tricky. Building images, as I just mentioned, is really tricky. All of these things require quite significant client-side logic, and none of it is documented. None of it is sort of written down anywhere, and so I've had to reverse engineer the Golang client to understand that. So, the official Docker client library for Golang, implements all this stuff. It takes care of all of it for us, nice and easily. And there is no fully featured Docker client out there for Kotlin or the JVM in general. Some of them do cover simple scenarios, but none of them cover all the scenarios that I need for what I do in Betect. So that's what I did. I ended up having to build my own. And so now, or previously, Betect had a battle-tested Docker client written in Kotlin that worked, had all the features I needed, and supports all these weird and wonderful things that the API does. However, maintaining that client and adding features to it was painful for all the reasons I mentioned before. So that poor documentation, that implied use of Golang, the really non-standard interactions, and that significant client-side logic that I had to reverse engineer. So it'd be great if I didn't have to do that in Kotlin and it could instead build upon the existing Golang client. And so that's what I ended up doing. I've rebuilt Betect's Docker client as a wrapper around the Golang client, and it's now in use by Betect's many hundreds of users every day, and none of them have complained, so that's a good sign. And yeah, despite all the sources of pain that I mentioned before, this approach has been working really well for me. I've traded the pain of poor documentation and the pain of implied use of Golang and significant client-side logic for more predictable pains that I mentioned on the previous slide. So things like memory management and developer experience and tooling and all that kind of thing. And because those pains are more predictable, I've been able to develop patterns and tooling and things like that to help me deal with those pains and make them less painful. So I've got two examples of that. The first is around tooling. So I mentioned before that you've got to make these two tool chains sort of work well together. I ended up building a Gradle plugin that can take some Golang sources and compile that down to static and dynamic libraries for each target. And then use Zig as the C cross compiler to satisfy CGO's need for a C toolchain. Who's heard of Zig, by the way? Okay, a couple of you, awesome. For those of you who haven't heard of it, it is a really cool language in its own right. But one of its coolest features is that it can act as a C cross compiler, and it largely just works. which is really, really cool. Like for those of you who've ever tried to do cross-compilation, you know it's usually a pain. Zig, it actually kind of works, and it's really nice. So yeah, give it a go if you haven't seen it before. The other thing I've spent quite a bit of time investing in to make my life easier is looking at making memory management easier. And to do that, what I've done is I've built a small code generation tool that takes in the definition of structs in YAML, like this. So for example, here we've got an arrow type that has a type and a message, both of which are strings. And from that single YAML definition, it generates a bunch of different things that I need. First of all, it generates the corresponding C definition. And it will translate the types for me automatically. It will generate C functions to initialize and free pointers to that type. So again, like it will allocate one using malloc, and then initialize it, and then I've got another one that I can use to free it when I don't need it anymore. It will also generate Go functions to convert from the Go types to the C types really easily. So for example, here we can initialize a new error pointer, and take in the Go string types, so I can keep the sort of the messiness of C contained in this method, and the rest of the Go code base is relatively clean. It also generates the corresponding JVM class definitions. So similar to what we saw before, we get a class that looks like this from that YAML definition. You'll notice that one big difference here is that this one implements auto-closable as well, which means that we can use the try with the resources pattern to make sure this is cleaned up properly. And yeah, that means that it then goes off and calls that C method we just saw before to free the memory associated with it as well. And it will also generate the corresponding JVM interface definition for the methods that were generated automatically. Another part of it also takes in the C header generated by CGO and translates those methods as well. So you end up with one giant interface with all the different methods. And I don't have to write any of that myself, which is awesome. And yeah, that saves me from a bunch of tedious and error-prone work. So that's why I'm doing this. And those are the things that I've had to do to make it work. To recap, you can use C as a bridge between different languages. Both flavors of Kotlin can call C functions, and Golang can both call C functions and expose Go functions to C functions. Try saying that 5 times fast. There are lots of ways to do this on the JVM. Each with different trade-offs. I would recommend JNR as a sensible starting point unless you've got particular constraints. With Kotlin Native, it's really straightforward though. And yeah, please don't actually do this. That's all I have to say. We've got tons of time for questions. If you're interested in looking at the example I showed you, it's up on GitHub. And if you're interested in the Docker client library I mentioned before, that's available on GitHub as well. Thanks. Yeah, any questions?
Thank you for your talk. So when in the last part that you showed where you were generating the code from the YAML, is there a way to keep that in sync? So if you want to update the structs, do you have to sort of copy that in again, or is there an easy sort of tooling to
so like if I was to make a change to that YAML, does it generate everything else automatically? Is that what you're asking?
Yeah, exactly. Like, or you know, vice versa. If you went and made a change to the Kotlin struct, or also the Golang struct, or something like that, if you can get that back out into the YAML and then synchronize it to the other side.
Right. So the YAML is the source of truth, and so if you change the YAML, it will generate everything else again. And that's built. I've built that as a Gradle task that runs automatically as part of the build process. So that stays in sync with that. And yeah, if you made a change to any of the other source files, they would get overridden. So yeah, you'd have to change the generation tool to do whatever you needed. Thanks. Anyone else? I swear I haven't planted questions with people that I know.
Just in terms of the Docker HTTP versus Golang interfaces, what sort of maintenance burden do you think you've traded off in terms of likely changes from the Docker side that you'll need to keep supporting?
I think one of the big ones was BuildKit and the image builder. So the first version of Docker had, for those of you who aren't familiar with the history, like the first version of Docker had a built-in what's called a legacy builder now, and then they came up with a newer, smarter way of building images called BuildKit. the trade-off with that is that it requires significant client-side logic to make that smartness work. And so yeah, one of the things that I am saving myself is having to implement all that client-side logic. And as I improve that and continue to evolve it, like I'll have far less to work on to keep in sync with that. Anyone else? No? Awesome. Well, yeah, thanks so much for coming. And yeah, I'll be around all day if you've got any other questions.
Round of applause.